Okay, start.
Right. Hey everybody. So you get to see me live this time. So this time what I want to do is do a volume of revolution, but this time spinning around the y-axis instead of spinning around the x-axis. So let's look at these two equations. We'll have y is equal to 1/3 x, and also, let me color code it. So that'll be black, and then in red we'll do y is equal to the square root of x. So what do these look like? Well, 1/3 x, that's just a straight line, positive slope. So, and the y-intercept is right at 0 through the origin, so something like this. And the square root of x, which is in red, well, that's just your sideways parabola, so a radical graph. So something like that, also connects at the origin. So we sort of get one of the intersection points for free right there. Our goal is to take this region that's bounded by these two graphs, so this region right here, and instead of spinning it around the x-axis, which is what we did before, let's spin it around the y-axis. So one thing I like to do when I'm spinning around axes, and we label this, so this is the y-axis, this is the x-axis. So one thing that's sometimes teachers do to indicate a revolution is to do this kind of symbol like that. It's like an arrow spinning around the axis you're doing. So if I wanted to go around the x, I would have put that little spinning arrow here, but I'm going to put it around the y. So I'm taking this kind of like it was like a piece of paper, and going around also goes crashing through the whiteboard here, comes out the other side. So if you were looking at it flat on, you would basically think it was a cone. But then when you looked at it from the top down, you realize, oh, there's like this weird puffy thing taken out of the cone, right? It's being caused by this. If you just look at it straight on, you'd only see the outside part. I'll try to draw this. So when this green part spins around, it's going to come out, so coming in, sticking out at you here, coming in over here, so this kind of looks like that. And the red one, if I had computer animation, I could actually have it do this, so instead you're stuck with me. And then, of course, the green stuff. So you gotta do the green stuff this way. And it's this entire, it's not just these two green petals, it's also sticking out all the way. I'm just drawing what I can draw on the whiteboard. So, all right, we're spinning this around the y-axis. When it spins around, let's look at sort of a representative slice. So I'll do the representative slice in blue. So we pick some y-coordinate between here and, well, whatever this top part is. I guess we haven't figured that out yet. So why don't we do that before I do the representative slice? So to figure out where we're stopping or chopping up with the y-axis, we have to figure out that coordinate right there. So to figure out the intersection of two curves, we set them equal to each other. This is stuff we've done before. So we get 1/3 x is equal to the square root of x. Let's go ahead and square both sides. If you square both, actually before I square both sides, I don't like fractions. I'm going to move that over. Not necessary, but now I don't have to write two different things there. So I square both sides. So that side squared is x squared. Got to square these. I don't need to FOIL anything out or do Pascal's triangle because there's no addition or subtraction here. So I just square each thing. So that becomes a 9. That becomes an x. A typical mistake that students make is then try to cancel x's from both sides. But don't actually do that because then you're possibly dividing by 0. So the real way to do this is scoot this over, factor out the x. So using the multiplication principle, so either that is 0 or that is 0. So those are the two possible x's that give you the same y-coordinate. And I'm realizing now I shouldn't have really called them both y. I should have given them names. So let's call this one f of x and this one g of x. So I could say that when I do the graph, on this graph, the y-coordinate for the red is being determined by g of x. And here, the y-coordinate on the same graph is being determined by f of x. So, all right. So we've now figured out that these two graphs have the same y-coordinate when x is 0, which we already kind of knew, and also when x is 9. probably not a bad idea to do a double check. It's clearly true from the graph, but let's actually just double check because there's always the possibility of having introduced extraneous equations here. So just a little double check. If I look at f of 9, so this is going to be our straight line. So that would be 1/3 times 9, which is 3. On the other hand, g of 9 would be the square root of 9, which is 3. Not plus or minus 3, just 3. Radical sign means plus. So they both have the same y coordinate. So this tick mark up here is 9. This one here is 0. All right, so now let's go ahead and take our representative slice. So I pick any y coordinate I want between y and 9. So I'll just pick that one. So here's your typical y. So if I look at this slice, imagine I've got this kind of weird coney kind of shape, but with a little air hole kind of in it. So I take a slice right here. So when I chop it, let's just follow this segment as it spins around. And this is kind of what I did on the previous video, is I sort of followed a red dot here and followed the black dot here. So what's going to happen is, so pretend this is my blue segment, right? So the blue segment comes around over here. I'll even continue drawing it over here. And as it comes around, we can follow this red segment here at the tip as it spins around the y. So it's going to create a red circle, which also continues behind the whiteboard. And then you've got this black spot here. It comes around, creating a black circle there. So I'm going to try to draw this in 3D. It's not going to look really good. But this is it kind of coming around. This is behind the whiteboard there. That's why I made it dotted. And then here's the black part. This is the outside part you would see. You'd only see the red part if you looked inside this cone. The black part is what you'd see if you looked the outside. So there. I guess, yeah. Although, yeah, that's good enough. So this is the slice. Then all of this would be blue. So here's the blue segment coming around. All right. So what we need to do is add up the areas of all these different washers for every single possible y slice between 0 and 9. So we can set up this integral. We saw before when you add it up, it's just pi times the bigger, let's remind ourselves, the area of a washer is pi times the big radius squared minus the small radius squared. So here we're going to integrate from 0 to 9. And we're integrating with respect to y this time. This is why it makes it a little bit different from the last problem. So when we were spinning around the x-axis, everything was in terms of x's, and we had a dx. This time, we're spinning around the y-axis, and everything's going to be in terms of y's. So let's actually try to draw a face-on version of this washer right here. So this black circle is the outer circle. The air hole right here, that's the red part. That's going to be on the inside. And then we've got our blue segment right here. This is like an aerial top-down view of it. So this is the area that we want. So what's our big R going to be? So here's the center of our washers. That would basically be that spot right there. So this dot right there is that dot right there. So if I want to figure out what the big R is from here to here, what's big R going to be? Well, big R, this spot from here to here, equates to from here to here. So in other words, it's the x-coordinate of this black dot. So I know what the y-coordinate is. The y-coordinate is just y. But what's the x-coordinate? I need it as a formula of y's. Well, the black dot is on the straight line. Here's the equation of the straight line. So we've got y is equal to 1/3 x. What we want to know is, what's the x-coordinate? Because the x-coordinate of that point is how far across you went. So whatever the x-coordinate is in terms of y, that's what our big radius is. That's actually kind of the key idea right here. This spot from here to here is the x-coordinate of that spot. But we need to write it in terms of y's. So the x-coordinate on the line, I just move this 3 over. So x is equal to 3y. So that's what my capital R is. So notice the big radius changes based on what your y slice is. So if your y slice is down here at y equals 0, you're out. That's not a very good example. That's at 0. But for example, suppose I chuck it at 1. So if I were to take the slice at 1, then my r would be, the big R would be 3. The higher up I go, the bigger the big radius is. So, all right, so r is equal to 3y. Big R is equal to 3y. What about the small r? So the small r on this picture goes from here to here. So in our three-dimensional picture, that's this part. It's our little air gap right here. So this is just the x-coordinate of our red dot. So what's the x-coordinate of this red dot right here? Well, this red dot is controlled by the radical graph, the square root of x. So in this case, we have y is equal to square root of x. We want to know the x-coordinate for a given y. So we got to write, what is this as a formula of y's? So we would just square both sides. So that gives you x is equal to y squared. I kind of flipped the order there. But. All right, so x equals y squared. So that is our small radius. And now we're ready to do the integral. So the formula for our volume, so our volume is going to be equal to the integral from 0 to 9 of pi, which I'm going to pull outside the integral, of the big radius squared. So the big radius is 3y squared. Take away the small radius, which was y squared, squared. It's a little complicated. I got a squared and a squared here, right? So this squared is coming from the fact that I have to square the radius. This squared is coming from the fact that was actually the formula for our small radius. So, all right, I'm going to switch to a more neutral color here. Let's just do the whole thing in green. So this is pi times the integral from 0 to 9 of, well, 3y squared. I got to square everything, so that's going to be 9y squared. A squared squared means you multiply the exponents. So 2 times 2 is 4, so y to the 4th. This is all dy. Technically, there should really be parentheses around here, but I guess I'll put them on. All right, so at this stage, easy peasy lemon squeezy. We just go ahead and do the integral. So power rule, add 1, divide by the new exponent. So add 1 to 2 becomes a 3. Divide by 3, I'm just going to go ahead and cancel 9 over 3 is 3. And here is just minus 1/5 y to the 5th. And we're sticking it in between 0 and 9. And at this stage, really, I would just get out a calculator. I'm just going to move this over. I can't actually move it over, but separate it out. So when I plug in 9, let's see. I think we're past the stage I can do this in my head. So 9 cubed, 9 times 9 is 81. 81 times 9 is 729. And I have to do 3 times 729. Yeah, you get a calculator for that. And then we have to subtract what we get, 9 to the 5th. Horrible, I don't know what that is, but whatever 9 to the 5th is, you divide it by 5. It's not going to go unevenly. But then don't forget, you have to subtract off what you get when you plug in 0. So when you stick in 0, because of the stick, well, that's just 0. Not too exciting there. And you're going to get some number. So I'm just going to go to my calculator and see what this number is. I don't know why I didn't do that earlier. So let's see. 3 times 729 is 2187. 9 to the 5th, which I have no clue what that is. Yeah, some big number. Divided by 5, so 11,809 and 4/5. And don't forget, all of that is times pi. So if you want to keep things exact, you could say it is 9622 and 4/5 pi, which is approximately, I'll just go ahead and multiply the pi on there, 30,230.918. And technically it's 9177, but for AP you just do 3 decimal places. And what about units? Well, I didn't give any units in this problem. I could have said, oh, well, this is some vase, and this 0 to 9 is 9. 0 to 9? Uh-oh, did I make a mistake here? I did make a mistake. So, oh, my cameraman didn't catch me. Cameraman, what was the mistake that I made that he was too shy to make?
The y-axis.
Uh-huh.
It should be 3.
It should have been 3, right? So, we'll fix this in post, as they say. Actually, probably not be fixed in post. So, yeah, I realized here when I looked at the lines, like, wait, how can this be 9 and that be 9? Something went wrong. So, we'd figured out, let's see if we can identify where the error was. So here we said 0 and 9, but this is the y-axis, not the x-axis. So we had to go back, which was like, wait, how can this be 9 and that be 9? Something went wrong. So we'd figured out, let's see if we can identify where the error was. So here we said 0 and 9, but this is the y-axis, not the x-axis. So we had to go back, which we didn't, and figure out what the y-coordinate is. So you could either do the square root of 9 is 3, but we did it over here. So f of 9 was 3, g of 9 is 3, and then for some reason, I wrote a 9 here. I was seeing if people would catch it. That was the plan. So let's just go ahead and fix it. Thankfully, we don't have to rework a whole lot of stuff. So that'll be a 3. I actually make mistakes like this all the time when I do my iPad version, but I edit them out. So here you get to see me do the edits. So this would be 0 to 3, 0 to 3, 0 to 3, which, all right, let me erase it. Oh, this pen is hard to erase. So much easier just to cut on the iPad. All right. So let's see what we really get. So the number's really smaller now. I think I can handle it. So 3 cubed is 27. 27 times 3 is 81. So 81 minus 3 to the 5th. Can I do 3 to the 5th? Well, I know 3 to the 4th is 81. And then 81 times another 3 is 243. So this is 243 over 5. You have to take that again, still plugging in 0. All right. So at this stage, I'll get to the calculator. No, let's not use the calculator. It's small enough. So 81 times 5, that's 405. So this is 405, take away 243 all over 5 pi. When it comes to subtraction, now I really am going to use the calculator. I'm done with making mistakes for the day. So it's 162 over 5 pi. So that would be the exact answer. And if we were to put this as an approximation, we would get, this is approximately equal to 101.788. And as far as units, if I had said this was in inches, then this would actually be in cubic inches because we're doing volumes. So, but I never gave any units, so I'll just say units, well, 3 here. The way you read this is cubic units. I know it looks like units cubic. But, all right, so that's an example of revolving something around the y-axis. It works very similar to revolving something on the x-axis. The only key difference is all your variables are in terms of y. All right, you can stop.